Okay, so today we're going to consider the duality of a linear program. So in optimization, every optimization problem has a dual form, especially for the constraint optimization problems. We can consider dual problem as a mirror of the primal problem. So today we're going to focus on the case of linear program. Consider the primal problem, which is the original linear program problem, and also its dual problem, which is also linear program. Okay, so first to recall that the primal linear program is the one that we discussed before. Here we're going to make a slight change of the original one. So originally we have a linear program that is given by the minimization problem, where the constraint objective function is c times x, and the constraint is the ax equals to b, and x is greater than or equal to 0. Okay. Today we're going to consider a slightly different one. We change the equality constraint to an inequality constraint here to this one, and we're going to consider this one later on, this original one later on. But let's first consider the this modified linear program, and we call this primal linear program, where the objective function is the same as before. The inequality constraint becomes the inequality constraint here, and the x is bigger than or equal to 0. It's the same as before. Okay, so we call this a primal linear program. And then there's a dual problem of this linear program, which is given by the following one. Okay, so here the variable we're trying to optimize is a lambda instead of the x. Okay, so x is the primal variable in the primal problem, and this lambda is called the dual variable in this dual problem. Okay, and the vector at lambda, so originally this x is a n-dimensional vector, so the x is in Rn, and here this lambda is in Rm, where m is the number of rows in the matrix A. Okay, so it is still a linear program in the sense that the objective function is b times lambda, where this b is exactly the b here. Okay, and also the minimization problem is changed to maximization problem. So instead of minimizing this, we're trying to maximize this. Okay, and also the constraint, so ax greater than or equal to b, is changed to the A transpose times lambda less than or equal to C. So here it's like that we switch the role of C and B, and we take a transpose of A, and that becomes A transpose here. And the greater than or equal to becomes less than or equal to. Okay, and this is the same as before. Okay, so now you can see that the lambda is an m-dimensional vector. Originally the A is a m by n matrix, and A transpose will be n by m matrix. So originally A looks like this. This is the A. Okay, and then we multiply by a long vector, n-dimensional vector x. And now the things change. This is the A transpose. It has n columns, n rows and m columns. It's multiplied to this lambda. This is lambda here. And it's less than or equal to C, which is this long. Okay, so that's the dual problem. Okay, as I noted here, so how do you get this dual problem from the primal problem? First, change minimization to maximization. Then switch the C and B as here. And replace A by A transpose. And then change this greater than or equal to less than or equal to. Okay, so that's all the things I need to do to change the primal variable, the primal problem into the dual problem. Okay, now the question is why we're doing this, and why this is why we call these two problems primal and dual problem. Okay, so the idea is this. Now let's focus on a kind of a different but a related question. It's a simpler then it's a building block of what we're going to do next. So now let me ask you, so suppose we have a vector b that is greater than or equal to 0. Okay, so b is just considered as any like an m-dimensional vector. So b is Rm. So b greater than or equal to 0 means that all the components of b are non-negative. Okay, now we'll consider this problem. If I'm going to maximize the lambda transpose times b, it's just inner product of lambda and b. Both lambda and b are m-dimensional vectors. And I'm having the constraint here. So let me write it in this way. Lambda is greater than or equal to 0. Okay, so apparently the objective function is equal to lambda 1 b1 plus lambda 2 b2 all the way to lambda m bm. Right? This lambda 1 through lambda m are the m components of the vector lambda, and the b1 through bm are the components of b. Okay. I'm sorry. I should change this to less than or equal to. Say suppose b is non-positive, so all the components of bi's, the bi's are all less than or equal to 2 for all the I. Okay, the question is, what is the maximum value of this, and what is the maximizer of this problem? But now the variable is lambda, and the objective function is lambda transpose times b, or inner product of lambda and b. And apparently, as we saw, I can see this is greater than or equal to 0. Sorry, it's less than or equal to 0 because bi is less than or equal to 0, and lambda 1 is greater than or equal to 0. Okay, so that means these two together must be less than or equal to 0. And that is the same, that is true for every term we're writing here. Okay, so this is also less than or equal to 0, this is also less than or equal to 0. So apparently if I want to maximize this, the best I can get is 0, because every one of them is less than or equal to 0. Okay, so next question. Because every one of them is less than or equal to 0, to reach the maximum value equal to 0, that means every term has to be equal to 0. Right? If any of them is strictly less than 0, then the sum will be strictly less than 0. So if I want to reach the maximum value of this objective function, the only way I can do is to make sure every term is equal to 0. Okay, so that means lambda I bi must be equal to 0 for all the i's. Let me see that lambda star is the optimal solution for this problem. So the lambda I star is the ith component of the lambda star. Okay, so the optimal, so if lambda star is optimal, then the lambda I star times b must be equal to 0 for all the i's from 1 to m. Okay, so what this tells us is that if bi is negative, then the lambda I must be equal to 0. The lambda I or lambda I star must be equal to 0. Okay, and if bi is equal to 0, then lambda I can be any positive number or non-negative number, because the product of these two will be still 0. Okay, so that means we can easily solve this problem. That maximize the lambda transpose times b, or inner product of lambda b, under the constraint lambda is greater than or equal to 0. The solution is that if bi is less than 0, then lambda I star must be equal to 0. And if bi is equal to 0, then lambda I star can be anything. Right? That would be the solution to this problem. Okay, and now let's look at what is the objective function value. If, as we said earlier, the optimal objective function will be equal to 0, because I can just set for the corresponding bi, or just set my corresponding lambda I in this way, then we can guarantee that all these lambda I bi, they are equal to 0. The product will be equal to 0. And that means all of these terms are equal to 0. And so that means this objective function is 0. Okay, so that is the case where the b is actually less than or equal to 0. What if the b is positive, well, is not less than or equal to 0? That means one of the components of b is positive. Okay, so now let's consider this case. So b is not less than or equal to 0. That means there exists some bi greater than 0. Okay, and then let's consider the same problem of maximizing this. Lambda is greater than or equal to 0. And it's the same, the inner product of lambda and b, it's just lambda 1 b1 plus lambda I bi plus lambda m bm. Okay, now the bi is positive. Lambda I, as long as it is greater than or equal to 0, is fine, right? And now I'm trying to maximize this. So what we can do is, well, I don't even need to care about any lambda j for j not equal to I. Okay? I don't care any other terms because I just need to focus on this. Since bi is positive, I can just make my lambda I arbitrarily large and this will blow up, right? This will go to positive infinity. And that will maximize my objective function. So what can I do? It doesn't have a maximizer here because I can make this, make this lambda I tending to infinity, positive infinity, and this term will be positive infinity. And I don't really need to worry about anything else. I can just set them to 0, right? Any other lambda I to be 0, and this will be just the infinity. Okay, so that will be the case for when the b is not less than or equal to 0, or if one of the components of b is positive. Okay, so in summary, when I consider the lambda I, the transpose, lambda transpose in b, maximizing it, this is a function of b. It is a function of b because for every b I can decide what's the value of this. And when b is less than or equal to 0, I know the value here must be 0 because I showed earlier that if b is less than or equal to 0, then the best that we can get for here is that everything equals to 0. Every term is equal to 0, so the sum is equal to 0. And we show that if this is not the case, or otherwise, if one of the components of b is positive, then this becomes that. Okay, so that is the conclusion that we just made. Okay, now how this is related to the original problem, or the primal problem linear program and its dual. Okay, and here's the connection between them. Let me erase what the derivation is. Let's just keep the claim or conclusion at the bottom. Okay, now we have this. Let me move this to the top. Okay, so I have this information now. Let's look at the primal problem. So I can think that the primal problem is this. I'm minimizing the C transpose X, and I want my X to be greater than or equal to 0. That's no problem. I always want it to be non-negative. And I'm going to add this function. So this function is called px. So what is px is? The px is defined to be 0 if ax is greater than or equal to b. And if not, then the value here is infinity. Okay? So now you can see the relation between this function. I just artificially define it this way. If x satisfies this inequality, then the px takes the value 0. And if not, if any of the ax, the vector ax, any component of the ax is less than b, the corresponding bi, then this will take the value in positive infinity. So you can see that these two are the same. Well, since we have this information now, we know that this is nothing but equivalent to the b minus ax less than or equal to 0, right? I can replace this one by that one, it's the same. So that means I can replace this px by the maximum of lambda greater than or equal to 0 and the lambda transpose. Here the b vector, it used to be the b vector here when I multiply the b vector, but now this is the b minus ax. Okay, I want to check if b minus ax is less than or equal to 0. So I can just replace that by b minus ax. Okay, and due to the derivations we had earlier, if I define my px to be this, for every given x I compute this value, I realize that it's nothing but just this. And now I can put this back in here, because this will be the p function. And what this p function actually is, as we said, if the x satisfies, so what is px? So if cx, c transpose x times plus bx, we know that if x satisfies the condition that ax is greater than or equal to b, or b minus ax is less than or equal to 0, then this is just px is just 0, and that means this is just c transpose x. Okay, and if it's not, then this is infinity. Okay, so if now I plug this back into the minimization problem, as you can see, I definitely don't want my px to be infinity because I'm trying to minimize it. If this is a positive infinity, then there's no way to minimize it, right? We're done then. We cannot find a minimizer. So it's definitely not a minimizer. So the only case that this is still, we can still get a meaningful minimization is that the px is not infinity. And if it's not infinity, that must be 0. And that means this whole thing will be just a c transpose times x, like the one here. Okay, so it's like that we put the constraint, the ax greater than or equal to 0, into this px. This px is sometimes called the projection. Means that if x is actually inside the set here, then the px is just 0. But if the x is not, then this px is positive infinity. Okay? Or someone call it the indicator function. It tells that if x is inside the set described by the x greater than or equal to b. If it's inside, then this is 0. And if it's not, then this is positive infinity. Okay, so that means the problem of minimizing c transpose x plus px, x greater than or equal to 0, is exactly the same as minimizing c transpose x, x greater than or equal to 0, and ax greater than or equal to b. Okay, and now you can see that this is exactly the same as the primal problem here. We're minimizing the c transpose x subject to the constraint that the x is non-negative and ax is greater than or equal to b. And that's exactly the primal problem right here. Okay, so now let me further move forward and see how do we derive this dual problem from this primal problem. Okay, so again, let's let me still just keep the bottom and recall what we have. We can move it here. Okay, and now let's see. The px is shown to be the maximum of this value. So let me plug this into this. I will get just the top row. It becomes c transpose x plus the maximum lambda greater than equal to 0, lambda transpose B minus AX. Okay, so don't be confused with the mean and max in here. It's very common in optimization. So what this maximum means is that for every given x, we're going to find the maximum value of this. Apparently it depends on lambda, but whatever it is, we just compute the maximum value of this. So this actually can be treated as a function of x, and that is the px we just showed. It's a function of x, and then we're just minimizing the C transpose times x plus this px. Okay, so that's the same problem. Okay, so now I will have the minimum of x greater than or equal to 0, and the maximum, I put it outside. It doesn't matter because this first term here does not depend on, this Cx does not depend on lambda at all. Right? So when I put this inside here, it doesn't affect my maximizer at all, and the objective function is nothing but just the same objective function here plus the C transpose times x. Right? As I said, this doesn't depend on lambda. So I put them together, C transpose x plus lambda transpose B minus AX. Okay, so now let's switch the min and max, and we'll see that when we switch this here I'm going to have this C transpose X plus lambda transpose B minus lambda transpose AX. Okay, and here I will have the maximize of lambda greater than or equal to 0, min of x greater than or equal to 0. Here I will collect everything about this in front of x. So that's actually, I put x first, that's x transpose, and then C minus A transpose lambda. Okay, and then plus lambda transpose B. Okay, so here, let me focus on this part, because the last term does not depend on the x. So I can treat this thing here as a function of x. Okay, it's a function. It's a function of lambda. For every fixed lambda, I can compute this framed minimization problem here. So just to find the maximizer of x such that this one is minimized, and then we add this function of lambda. So this whole thing here can be considered as q lambda. So this whole thing here is just q lambda. Okay, now the question is, what is q lambda is? What is q lambda is? Okay, let me erase this and figure it out. So as we said, this is the minimizing the x greater than or equal to 0, x transpose C minus A transpose lambda. Okay, and this is the same as we said, it's minus maximizing x greater than or equal to 0, x transpose of A transpose lambda minus C. Okay, the reason is minimizing some function is the same as minus maximizing of the negative of the function, right? That's minimizing, say, f of x for whatever x is in omega. It's the same as maximizing the negative of f and a negative outside, right? You can easily show this. Okay. Well, that's what we applied here. This objective function is f of x. So we put negative sign and essentially putting the negative sign in the parentheses. And we'll get this. Okay, so now recall that this part, previously we showed that if we are maximizing some Here I have the maximizing the lambda transpose b for lambda greater than or equal to 0, then this becomes either 0 or positive infinity, depending on the b. If b is less than or equal to 0, we have 0. If b is not less than or equal to 0, then it will be positive infinity. Okay, and this will be the same, right? So for this part, this will become 0 if A transpose lambda is minus C is less than or equal to 0. And they will be positive infinity otherwise. Okay, it's just for this part without the negative. Okay, and with the negative it's the same, just that if this is true, they will be just taking value 0. Otherwise, you take the negative infinity. You take the value negative infinity. All right. So now that's what happens to this qx. This whole thing is just the q lambda. So the q lambda will be equal to negative of this thing, which is equal to that. So in summary, the q lambda itself, as I just mentioned, will be just either 0 or negative infinity. Okay. So let me just write it here. Okay, the same as A transpose lambda minus C less than or equal to 0. It's the same as this, and then this. Okay, so that's my qx. I'm going to plug this right here into this. So I know what this one is. So now I'm going to just continue writing it. So the maximizing the lambda greater than or equal to 0 for q lambda plus lambda transpose b will be just equal to maximizing the lambda transpose b, or b transpose lambda. Let me write it that way. In the constraints lambda greater than or equal to 0, I said that this is the plus qx. So if qx, q lambda, if lambda satisfies this condition, it will be just equal to 0. And if it's not this, then it will be negative infinity. Then this thing here will become negative infinity. And since we're maximizing it, there's no way that we can maximize it if this is negative infinity, right? That means the lambda must not violate this. Must be one of the points that satisfies this. Okay, so this means that the q lambda is essentially just constraint of that lambda greater than or equal to 0, and the constraint induced by this q lambda is just A transpose lambda less than or equal to C. Okay, and that is exactly the due problem. Since we're maximizing the B transpose lambda, subject to constraint that lambda itself is greater than or equal to 0 and A transpose lambda is less than or equal to C. Okay, and that is the reason why these two are the same. Okay, so it's just the same thing, and we look at it from different angle. Okay, so that is the due problem. Now, as you can imagine, we show that the due problem of a primal linear program, and the question is, the due problem itself is a linear program, and what is the due of the due problem? And you can expect that the due of the due is the primal problem itself. Okay, and to show that, let's look at the due problem. Try to see what is the due of this problem, and it turns out to be just this one. Okay, so let's first recall the due problem. Originally, the due problem is the maximizing the B transpose lambda, and the constraint is that A transpose lambda is less than or equal to C, and lambda itself is greater than or equal to 0. If we want to consider the dual problem of this, we first need to convert this into the standard form of the dual problem, to the standard form of the primal. So we think that this is actually a primal problem here. So to get a primal problem, we need this kind of form, right? We need minimizing a linear function, and here we need is greater than or equal to 0, or greater than or equal to b. Well, to reach that, that's not difficult, because maximizing this is the same as minimizing the negative b transpose times lambda. Well, the objective function we still need another negative outside of the minimization, but it doesn't affect our maximizer here or minimizer here. It's the same. And here again, I'm going to replace the a by the negative a, which is multiply the negative sign on both sides, and we'll get this. Okay, just put negative sign on both sides, and then also lambda is greater than or equal to 0. So now you can see that the dual problem can be considered itself as a primal problem just by putting negative sign in front of a, b, and c, and then we have a primal problem. And then according to what we did before, so this is repeating what I have here. Just replace just the same thing. Okay, and remember that to convert this into the a dual problem, we need to change this to maximization and switch the negative b and negative c. So that's how I get this. And I call that, this is my primal variable now. The dual variable I call it x. I can call it any other variable, but this is just a symbol right now, right? So the symbol, I just call it, I just let the x to denote it. And here I'm going to take the transpose of this, that becomes negative a. Okay, now I have this. And I'm going to switch this inequality into this. Okay, and x is greater than or equal to 0. So if I write my primal problem in this way, then the dual problem will be that. Okay, so now you can see maximizing this is the same as minimizing the C transpose X. Okay, which is to put the C negative outside, that will become minimization. So that's how we got this line. And then this, again, when we put negative sign on both sides, we'll get x greater than or equal to b. And also this x greater than or equal to 0 is unchanged. So that's why this problem here is equivalent to this problem. Okay, it is the same one. And we show that this is the dual of this problem. So this is a dual. This is actually the original dual problem. We just write it such that it looks like it's a primal problem. But the dual of that is this. And then we show that this is equivalent to this one. So that means this is the new dual, and this is the original primal. Okay, and you can see that the dual of this problem is just the original primal problem. So the dual of the dual is the primal. It's just like the transpose of the transpose is the is the matrix itself, or the inverse of the inverse is the function or the matrix itself. Okay. Now let's consider the standard form of the linear program, because in the previous lecture when we talk about the standard form of the linear program and the simplex method, we said always start from the standard form of the linear program. In that case, we don't have ax greater than or equal to b, we have ax equals to b. So the standard form of the linear program is this. Okay, so let's consider the dual problem of this linear program. Here, the only difference is that the originally we needed ax greater than or equal to b, but here we have ax equal to b. And there is an easy way to convert this into a inequality. We just need to know that the ax equals to b means that the ax is less than or equal to b, and at the same time ax is greater than or equal to b, right? If we have both of this, we can show that x is equal to b. But the second one here, second inequality here, we can put a negative sign on both sides, and that essentially just become negative ax less than or equal to negative b. Okay, or in other words, the first one I can rewrite this as negative ax greater than or equal to negative b. Okay, either way. But now since I want greater than or equal to, so let's convert this ax less than or equal to b into negative ax greater than or equal to negative b. And I also have the ax greater than or equal to b. So altogether, we just doubled the number of equations here, which convert this into inequalities. Okay, convert this into inequalities. So essentially, as I said, this is this equality constraint is equivalent to ax greater than or equal to b in negative ax greater than or equal to negative b. And this is equivalent to saying that I would stack this a and negative a because they are both they both have n columns, and then I multiply by x, and this is equal to the, or is greater than or equal to the b and negative b. So this will be my new a. This will be my new a, and this will be my new b. Okay, and then we can apply the dual form before. Okay. So apparently, as I just repeat, I'm going to write the current standard form of the linear program. We said it's just minimizing this, subject to the ax equals to b, and x is greater than or equal to 0. I said this is equivalent to minimizing the c transpose x, subject to the constraint that a negative a times x is bigger than or equal to the b negative b, and then also have the x is greater than or equal to 0. So this is what I treated as the primal problem. I treat this as my primal problem. Okay, if this is my primal problem, then the dual problem will be just we're going to introduce the dual variable lambda. But right now I call this lambda u and v, as there are two parts of the variables. Dual variable called u and v. Okay, so this together is the dual variable right now. The reason is that I'm going to switch these two. Okay, I'm going to switch these two. So there is one variable corresponding to the b part and another variable corresponding to the negative b part. So I call these two parts u and v respectively. Now, when I switch these two, this objective function becomes this b negative b. So it's just a transpose of this. Okay, it's just a transpose of this. And the dual variable I call the u and v as I just explained. And then that's the maximization, objective function and the maximization. And in the inequality constraint, I said that we need to switch these two. So I'll have c here, no problem. And I'm going to have the transpose of this. So that will be just, when I put the transpose of this, become a transpose and negative a transpose. That will be this. Okay, and also the u and v together is our variable, and we also need to change this into this. All right, so now let's see the dimension. To be very careful about the dimension, so the A is R m by n, it's m by n matrix. B is R m, C is Rn. Okay, so that means this one here is a R2m. Okay, and this is a row vector. And here, this one, it should be n times 2m, right? It should be R n by 2m. Okay? And this vector here is in 2m. Okay, actually u and v are both m-dimensional vector. The c here, as before, is just Rn. Okay, so that's the dimension of this vectorial matrix. Okay, so now this is the dual variable. Okay, and now let's write it out I have explained the dimension. Let me erase it just to make it clear. So as we said, this will be just a B transpose times U minus B transpose times V. That's the objective function. We're maximizing it. Okay, and the constraint is that A transpose U minus A transpose V less than or equal to 0, less than or equal to C. And also that U and V, U greater than or equal to 0 and V greater than or equal to 0. Okay, so interestingly, the U and V, except for the constraint, the U and V, they come together as U minus V, because here this is just the B transpose times U minus V. Remember, the U and V are both m-dimensional vectors. Okay, and this become just A transpose times U and V, U minus V. So the problem is essentially just maximizing the B transpose times U minus V subject to the constraint that A transpose times U minus V is greater than or equal to 0, or greater than or equal to C. And then U, V greater than or equal to 0. Okay, well, we're only concerned about the U minus V, right? Because only U minus V need to be participate into the objective function and also this constraint. So as long as U minus V is satisfies this, then we're actually maximizing this with respect to U minus V. And we'll have the constraint U and V are both non-negative, but U minus V can be anything, right? The U minus V can be anything, so that we can just ignore this, but just treat this as lambda and this as lambda, and then we're just maximizing lambda, and we don't have any constraint on lambda. Lambda can be positive, negative, or mixed, right? And that is why this problem here, if we subtract or substitute the U minus V by lambda, we essentially just get this. Okay, sorry, it should be maximizing. Okay, now that's the problem. We got the dual problem, and we don't have any constraint on lambda anymore. And this is the dual problem of the standard form of the linear program. That's the dual problem of this one. Okay, this one. All right, so now let's summarize what we got. We call the first case and the second case that we just discussed the symmetric form and the asymmetric form, respectively. The first case considered the primal problem looks like this, where we're minimizing the C transpose X subject to this inequality constraint and the X greater than or equal to 0. The reason we call it a symmetric form is because the dual problem of this primal problem is maximizing the B transpose lambda, where the constraint is similar, it's A transpose lambda time less than or equal to C, and C greater than or equal to 0. So as we said, we got this form by first convert this minimization to maximization. C and B are switched, so that's why we got this one. And also A is taken, we take a transpose over A, we get this, and then this greater than or equal to becomes less than or equal to, right? That's why we get this. And why we call it the symmetric is because we kind of have a pretty nice correspondence between the constraints and the objective function. Okay, that's the symmetric form. And then the one we just discussed is called the asymmetric form. And in that case, the primal problem is something we are more familiar with, where the same minimization problem, but the constraint, we have equality constraint for Ax equals to B, and the inequality constraint just for non-negativity of X. And in this case, we show that the dual problem is to maximize the B transpose lambda. So it's again just to switch these two. So we have the B and the C here, and the A is taking transpose, that becomes this. and this equality becomes this, less than or equal to. And we do not have the positivity constraint or non-negativity constraint for lambda anymore, because this is the derivation we had earlier. Is lambda is like the u minus v, although u and v are non-negative, but the difference of them can be anything. Okay, so that's why you can see that we don't have the same number of constraints in the dual and in the primal, so that's why we call this second case the asymmetric form. Okay, just because the dual has a fewer constraint compared to the primal problem. But since this one is what we were discussing previously, we just give the dual form for that. Okay, so now let's give a series of properties of the linear program or on this dual problem. Okay, so the first result is called the duality. Okay, the duality lemma says that if X is the optimal, is a feasible solution for the primal problem, and lambda is the feasible solution for the dual problem, then the C transpose X is always greater than or equal to B transpose lambda. So what do we mean by feasible solution? It means, let's say, for example, this case, we're going to say that X is feasible if it satisfies this. It doesn't have to be optimal yet, but at least it satisfies all the constraints. And similarly, the dual variable, this they need to satisfy this as well. Okay. So as long as X and lambda satisfy their constraints, then this must be true. Okay. So that means when we plug in X into the objective function and plug in lambda into its own objective function, this is bigger than equal to this. Okay, we can prove this for the asymmetric form only, and since these two can convert it to each other easily. Okay, so now consider the asymmetric form. In this case, the X and the lambda are both feasible. So that means the X satisfies this, satisfies this, the lambda satisfies this. So let's see if this one is greater than or equal to this. Okay, so now since it's X satisfies the feasibility or the constraints for the primal problem, so that means these two are true. And also, we should not have this one here. In the lambda satisfied the dual, it satisfied the constraint in the dual problem, so that means A transpose lambda is less than or equal to C. So now let's see that because of this, we can check the B transpose lambda. So the B transpose lambda, we know that the B equals to AX, so I can replace the B by AX. And now we have AX times lambda, and this becomes X transpose A transpose times lambda. Okay, X transpose A transpose then lambda. So I have this, and then this A transpose lambda is equal to the C. As we said that, it's less than or equal to C, because the X is a non-negative vector, it's greater than or equal to 0. Right? And this A lambda, as we showed earlier, this lambda satisfies the constraint A transpose lambda less than or equal to C. So that's why the A transpose lambda is less than or equal to C. So what do we have? You just imagine if I have a vector, I call it, say, I call it y. So y can be any, so let's say y and z. I know that y is less than or equal to z. And it could be positive, could be negative, could be mixed, could be anything. And when I multiply both sides by a non-negative vector, so this y minus less than or equal to z means that the y1, so here this means that the yi is less than or equal to zi for all the i's. Okay, the y less than or equal to z in here, that means the y multiply the x transpose on both sides. I'll get the x transpose y less than or equal to x transpose z. The reason is, remember that this x transpose y is x1, y1, all the way to xn, yn, right? And the x transpose z is just x1, z1, all the way to xn, zn. Okay? If you know that yi is less than or equal to the zi, then, for example, I can take the difference of the two. The x transpose y minus x transpose z will be just equal to x1 times y1 minus z1 plus all the way to xn times yn minus zn. Okay, and we know that this one is less than or equal to 0 because y1 is less than or equal to z1. So this is less than or equal to 0, but this is greater than or equal to 0. So the product of the two is less than or equal to 0. And that's the same for all the terms. So the whole thing must be less than or equal to 0. And that's why when you move this to the other side, you just have this. Okay, so now this y is like the A transpose x, A transpose lambda, and this z is like the c here. So that's why we have this. Okay, so if I have A transpose lambda less than or equal to c, and lambda is x is greater than or equal to 0 is a non-negative vector, then you can keep the sign, keep the inequality. Okay, next is the result. Suppose that we have two feasible points, x0 and lambda 0. Again, these are two specific feasible points. Again, they just satisfy the constraint. They do not necessarily satisfy, do not necessarily minimize or maximize their objective function yet. Okay, but if they are satisfied the constraint, at the same time their C transpose x0 is equal to B transpose lambda. Previously, we know that if this is true, then we must have this greater than or equal to. But if they're equal, then they just mean that both x0 and the lambda 0 are optimal for their own problem. Okay, both x0 and the lambda 0 will be their solution of their problem. Okay, so this is actually just a very easy derivation, their corollary from the weak duality theorem or weak duality lemma before, because that we know this is must be greater than or equal to 0. So now let's consider let's consider any primal feasible point x. So that means for any x satisfies the constraint, which is the constraint for the primal problem. We already know that because x is feasible and the lambda 0 is feasible here, so x is feasible for the primal problem. Lambda 0, we show that it's feasible for the du. So we know that this C transpose x is greater than the lambda transpose, B transpose lambda 0. Right? This is from the weak duality lemma above. And we also know that this B transpose lambda 0 is equal to this. So that means this is always greater than that. Now what this actually says is x is any feasible point. x0 is a feasible point. And we show that you plug in any feasible point into the objective function, you get C transpose x. That is greater than or equal to the objective function when you plug in x0 into it. But this means that the x0 reaches to the minimum value of the objective function because it is the best optimal. It is less than or equal to any objective function value when you plug in a feasible point into. So that means this is the minimum function value, and that means the C0 is optimal. Okay, the C0 is optimal, and we can easily show that the lambda naught is also optimal for its own objective function, for its own du problem, right? So that's the easy conclusion. So combining these two, we can show that if x and the lambda are both feasible, then this must be true. So we showed here, if x and the lambda are both feasible for their own problem, then this must be true. And if this is equal, that just means both x and the lambda are optimal for their own problem. Okay, so this must be greater than or equal to, but if it's equal, that means X is optimal for the primal problem and lambda is optimal for the dual problem. Okay, next. If the problem has a optimal solution, then the dual problem will also have an optimal solution. And also, as it's the same as we said before, the optimal objective function value will be equal, which means that what it actually says that if your primal problem has an optimal solution, say we call it X star, and the dual problem also has a solution, which we call at least once already called lambda star. And then when we plug in the C transpose X star is equal to the B transpose lambda star. Okay, and this means that their objective function values are the same. Okay, for the primal and dual. Okay, so how we prove this? Let's first consider the asymmetric form. Means that the primal problem has this standard form of RP, and in this case, we know that by the fundamental theorem of a linear program, we know there must be an optimal basic feasible point. This is what we showed in the previous chapter. We're looking for the basic feasible solution for the linear program, meaning that we're finding we know that the constraint of the linear program gives us a polyhedra, and the minimum must be achieved at one of those one of the vertices of the polyhedra, and that is a basic feasible optimal solution. Optimal basic feasible solution. So it's optimal means that it's the best solution. Basic means that it has m, at most m non-zeros. M is the number of rows in the matrix A, and it's feasible means that it satisfies Ax equals to B and also x greater than or equal to 0. Okay, so that's what we know from the previous chapter. And now let's say that suppose the A, we can collect or we can move around the basic columns of the matrix A. Remember what we did for the simplex method. The basic columns we call it of matrix A, we call it B, and the rest we call the other columns together we call it the matrix D. And then when we consider the basic feasible solution, then it will be only the variables corresponding to the basic columns are called the basic variables. We call it the basic variable xb, and the remaining should be just 0. And this x is the optimal basic feasible solution, right? So we know that if the primal problem has a solution, then we must be able to find such kind of a solution. Okay, and again, as I said, without loss of generality, we just shift around the columns of the matrix and shift around the components of the B. So make sure that the first m columns of the matrix A and the first m components of the vector x, they are corresponding to the basic variables. And now, let's say that we can just define our lambda to be this. So the lambda transpose is this. It just means that lambda is the transpose this. Itself is transpose this. But we just keep this form. The lambda is m-dimensional vector, and the vector lambda transpose is set to the CB times the B inverse. So the B is the B here. This CB is the remember that we have the C vector, and that has the CB part and also the CD part. Okay, it's just that in this case, it's just the first m components of the vector C is the CB, and the remaining n minus m components are called the CD. Okay, we can set our lambda to be this, and this is m-dimensional vector. And now we can see because we reached the optimal solution at this x, so that means the current RD or the last row of the tableau will be non-negative, right? That's where we're going to stop the simplex method. We cannot make any further progress or make any improvement, and that means the CD vector is greater than or equal to 0. But recall that CD vector is equal to the RD vector is equal to CD minus this. Okay, just recall the simplex method. The last row corresponding to the non-basic columns is equal to this. So the CD, as we said, is just we have the C. should write here. C, B, CD. So the CD, CB are corresponding to this, and the B inverse is the B inverse here, and D is the D here. Okay, now because we define the lambda to be that, so this thing is just lambda. So what do I have is just the CD, sorry, it's really CD transpose minus this. Okay, T transpose minus this. All right. And now because this is not negative vector, is greater than or equal to 0, means that lambda transpose times D is greater than or equal to CD. Okay, so that means this. So with this, we can actually show two things. We can now show two things. One thing is that lambda is feasible. The second is that it must be optimal. Okay, to show that it's feasible, we just need to show that since they were considered asymmetric form, we just need to show that A transpose lambda is less than or equal to C, and then the lambda will be feasible. And to show it is optimal, we can show that it's maximizing the lambda transpose B. And B, because of the theorem before, we show that as long as we can show that this is equal to lambda transpose B is equal to C transpose X for some optimal solution or for some feasible X, then this will be fine. This lambda will be optimal. Okay, for the feasibility, we check this. So lambda transpose A, we know that lambda is this, and the A can be written as the two parts, the basic columns and the non-basic columns. And then we multiply the lambda inside, because the lambda is equal to that, lambda transpose is equal to that. So it should be transpose. So lambda transpose is this. So I just replace that, and then we'll get this. So now this, when I multiply this to B, apparently I will just have the CB. And when I multiply this to D, I know that this multiplied to D, this is lambda. It times D is greater than or equal to CD. Right? So that's why, sorry, this should be less than, here, less than or equal to CD. Because when I move this to this side, I have a CD greater than or equal to that. So that's why when I multiply this to D, it's less than or equal to that. Okay, and then this is equal to the C. This itself is just a C vector. Okay, so that means that A transpose A, lambda transpose A is less than or equal to C. So that means lambda is feasible. And now we can just check if lambda is also optimal. To check that, we check the objective function value. We plug in this lambda, where lambda is defined here. So it's this is what lambda is. And when you multiply it to the B, we know that the B inverse times B gives us the current basic variables. So this part here is just the XB, it's the basic variables. So that's the XB here. Now we have CB times XB. So that means we're making the inner product of these two. And that's the same as making inner product of these two together, because this is just 0. When I multiply these two together, it's just giving me 0. So that's just this. Okay, so after this, we can show that the lambda transpose B is just equal to C transpose X. And that means this lambda is also optimal. Okay, so this proves the case for the asymmetric form. And then the symmetric form is similar. We just convert the symmetric form into the asymmetric form as we did before. And then we can, and to do that, it's slightly different from, we showed how to convert the asymmetric one from the symmetric one. But from a symmetric one to the asymmetric one is also not difficult. It's just minimizing. Remember that we have this subject to the AX. Symmetric form is this, right? And then X is greater than or equal to 0. So in this case, we can just introduce the slack variable or the surplus variable, which is the C transpose X, subject to the AX minus Y greater than equal to B, where this X and the Y are both greater than equal to 0. Are both greater than equal to 0. Okay, and then this will become a function minimization of both X and Y, the x, y together, stacked together is the variable, it's a primal variable, and we can apply this proof earlier to this form, because this is the standard form now, right? It's just like the x and y together is the variable. A negative identity is the a vector, is the new a vector, okay? And everything will just follow. Okay, finally we want to we can show this complementary slackness condition. What it says is, so if x and y, x and the lambda are optimal solutions to their own problems, so the x is the optimal solution for the primal problem, lambda is optimal solution for the dual problem, if and only if the following two conditions are satisfied. So this, first of all, this is the inner product of the C minus A transpose lambda and X. The other one is lambda, inner product of lambda and A X minus B. So these two are called complementary slackness condition. So if you recall, at the beginning of this lecture, we showed that this, remember that when we're trying to maximize the lambda transpose B for B less than or equal to 0, for lambda transpose B, lambda is greater than or equal to 0, if and only if this lambda I times bi is equal to 0 for all the i's. And that is essentially saying that lambda times b is equal to 0. And that's the, we should replace the b by ax minus b, and that will be this condition here. That's the condition here. And when we consider, so we can recall, we consider the other one, where the q lambda is this, then we say that at the optimal solution, this part is also 0. Okay, this part is also 0, which means that x times this is equal to 0. So that is the last this condition here. All right. So as long as these two conditions are satisfied, the x and the lambda are optimal. Okay. This is a sufficient and necessary condition to show that x and lambda are optimal solutions. So let's prove this. First, we prove this direction, which means that we know these two conditions hold. And let's see if the x and the lambda are optimal. Okay. So we are assuming that the x and the lambda are feasible. So just need to show that they're optimal as well. So they're feasible means that ax equals to b. So let's consider the asymmetric form. The ax equals to b in this case, right? So when you multiply lambda, we'll move this b to the other side and then multiply by lambda. We show that this is equal to 0. So that's this condition. Okay. I think I should say this direction first, and then this direction. So this means that x and lambda are assuming that for this first one, we're assuming lambda and x are optimal. Okay, we're assuming x and lambda are optimal. So ax equals to b because it's optimal and it must be feasible. So that's why we have this. And because they are both optimal, so we know that the optimal or the objective function, we plug in x and lambda, the objective functions will become equal, right? They are equal when they're optimal. So the C transpose x equals to B transpose lambda. But B is equal to AX, so we can replace the B by A times X. And once we have this, we can see that we can, this part is nothing but just the X transpose. So this part is equal to X transpose A transpose lambda. And that is also the same when I take the transpose on both sides, because this is a scalar here. Right, this is the inner product of the two vectors, so this is scalar. So I take the transpose of that. It will be the lambda transpose A x. Okay, and that means these two are equal. These two are equal, so I can move the two to the one side. So I have the C transpose minus lambda transpose A times x. It should be equal to 0. And this part here is just C minus A transpose lambda times transpose. Just this equal to 0. Okay, and that is this condition. So assuming that x and lambda are both optimal, we can get these two conditions. And then assuming these two conditions hold, then this one here implies that the C transpose x equals to lambda transpose AX. Okay, and this one here, so this one implies that, and this one here implies that lambda transpose AX equals to lambda transpose B. And now we have showed that they are both equal to this, so these two are equal, and that's why C transpose X equals to lambda transpose B. And if since X and lambda are both feasible, and if their objective functions are the same, that means that both of them are optimal. Okay, so this shows that given the two conditions here, we can show that X and lambda are both optimal solutions. Okay, this finishes the proof. Okay, so now as a conclusion to this chapter, what we have done is to show that a linear program has its dual form, which is also a linear program. So in practice, you can work on either one, as long as that one is easier to work with, because eventually the solution will be the same, or the objective function value will be the same. And this is a very nice mathematical property that reveals the deeper connection between the optimization problem itself and and its dual form. Actually, later on we're going to study the Lagrange theorem of the constraint optimization problems, and there we'll again see these primal and dual problems. And this is just, as I said, just like a pair that always born together. And by looking at the dual problem, it sometimes can give us a very helpful or useful insight of the primal problem, or vice versa. There are many exercise problems and also examples that are given. Some of them are given in the textbook, which asks you to convert the primal problem into the dual form, or from the dual form to the primal problem, and then solve it. But when we solve it, since both of them are linear program, as we did in the previous chapter, so the solution will be the same. Our way to solve them is the same as before. Just apply the simplex method, or revise the simplex method to them. So the actual solution step, no matter if it's a primal problem or dual problem, the solution step will be the same, because it's essentially just solving a linear program. I think that's all the essential techniques you have learned for simplex method can also be applied here. So so when you see such kind of question, you know that it's not really tricky. When you see a dual problem, you just think that it's not that special. It's just, again, just another linear program that you can apply your simplex method to. So I will not discuss anymore about solving the dual problem, because as I said, it's just another linear program which you know how to solve. It's just the core idea in this chapter is to show that how to convert a primal problem into the dual, or from the dual to the primal, and what is the connection between the two in the several properties that we just introduced. Okay, that concludes this chapter.